past several years, the model has become 10,000 times bigger with respect to model size. That require a lot of computing to process in the data center scale. And such scaling is even faster than the Moore's law, creating a big gap between the supply of computing and this demand of computing. And we worked on model compression techniques to bridge this gap between the supply and demand of computing by making the models smaller so that we can reduce the cost and improve the efficiency of modern AI computing, like in the data centers and also in the mobile devices, so that we can fit those gigantic models into resource-constrained hardware devices, like our phones, our watches, etc. This can also reduce the cost on those cloud computing in the data center scale. So we achieve this by model compression technique. I proposed this about a couple of years ago, consisting of two techniques. One is pruning, the other is quantization. So pruning can reduce the number of parameters in a neural network to reduce the redundancy and find those non-working neurons and weights. It turned out the human brain has this pruning process, where during the adolescent time, where the number of connections in our brain, the neurons in our brain, is decreasing rather than increasing. During the time of adolescence, when we are learning the most amount of knowledge in our lifetime. And the second technique is by using quantization. Rather than using 32 bits or 16-bit floating point, we can use 8-bit or even 4-bit low precision representation to represent each weight and each connection. And that can reduce the model size by 8 to 4 times. So we applied such model compression techniques, in particular quantization, to reduce the inference cost of large language models by using TinyChat. So TinyChat starts with a big large language model you can see on the left, which consists of 16 bits for each weight. Since the autoregressive inference is memory bounded, we can reduce the precision to only 4 bits by using the activation-aware weight-only quantization to turn a big LLM into a smaller large language model. But naively doing this will hurt the accuracy, so we designed carefully a technique to make it activation-aware to fully preserve the capabilities and the accuracies despite that we are compress it to only 4 bits. After that, we want to run inference for the compressed model directly. But computer systems has been byte-aligned since the 1960s. So we designed this TinyChat inference library that can natively run 4-bit large language model. So we prototyped this on a TinyChat computer, 3D printed. We asked it to give some attractions in Boston. It's telling us about Fenway Park, Museum of Fine Arts, Museum of Science, etc. And everything is running locally on this embedded device in the back. It's pretty small. It's powered by Jetson Ori Nano, which has only 8 gigabytes of memory. And after compression, we can feed it with only 3.5 gigabytes of memory. So this is running a language task locally on such embedded device, can preserve the privacy. We no longer have to send the data to the cloud. It also helps not only for large language model, but also visual language model to understand not only text, but also image and videos. Like here, we can ask, what is unusual scene? Is there any safety concerns? And our visual language model, quantized to only 4 bits, can accurately answer in real time. A similar case applied to many different scenarios, like in the factory. We can ask how many cars are jacked up. Using the same model, we can do zero-shot learning without having to fine-tune the model. But with quantization, we can fit this to run almost in real time on a Jetson Ori. So TinyChat And 4-bit quantization can not only work on image understanding, but also we can work on image generation. So image generation are very computationally intensive because we have to predict each pixel, and there are tons of pixels if you want to generate images. But after quantizing them to 4-bit, we can make it even possible to run on a laptop. So here we are running LoRa and also photo editing in real time to make it interactive on a laptop. We can draw a house, and then you can draw the house according to your, the lines that you draw. We want to further compress not only the model, but also we want to compress the image tokens so that the model can get smaller and the image tokens can also get smaller, so that when we are feeding those tokens to diffusion model for image generation, they can run faster. So but this is not an easy task. If we compress it too aggressively using the baseline approach, you can see the quality for both images is very poor. But we designed this deep compression autoencoder that can compress the number of tokens by 64 times 64, which is 4,000 times, and still well preserve the accuracy. Despite that, we can have 1,000 times less number of tokens. And we can feed fewer tokens to the diffusion model, such that we have a much smaller amount of workload, making it lazy to process, such that we can run diffusion models much faster. So conventionally, it runs about only 17 images per second, but now it can run much faster at about more than 300 images per second to generate images. And on top of that, we further want to improve the model, not only have a smaller weights, smaller number of tokens, but also consider a non-conventional transformer architecture, which the computation grows quadratically with the resolution, right? So we designed this linear attention so that the computation grows linearly with the resolution, so that if you want to generate 2x bigger image, the computation will not be 4x larger, but only 2x larger. So we propose this SANA, which is a high-resolution image generation fast. This model can generate high-definition, high-quality images very fast. It's 100 times faster than the Flux model, and all these images are generated. It's not real. Not only on linear transformer, but we try to design a non-diffusion model to use the autoregressive model to generate images. Autoregressive model predicts token by token. Just like languages, here we want to predict patches of images sequentially, similar to language. So this model can achieve 7 times faster speed than the conventional diffusion-based approach, where you have to iteratively do denoising. And using this autoregressive model, we can see the quality is matches quite well with the conventional diffusion models, despite being 7 times faster. And with all these efficiency techniques, like the SANA can greatly reduce the cost to only $0.0019 to run for each image on the H100 GPU. By spending only $1, you can generate more than 500 images. And it's so efficient such that we can also deploy such image generation model on a laptop. So this is running on a laptop to generate the image. Within every 1 or 2 seconds, you can generate a new image. We can also change the prompt to generate something else, like an astronaut riding a horse. Efficient AI computing also requires long context so that we can understand longer documents, longer videos, larger images. And unfortunately, that comes at a high cost of computing as well. In order to save computation for long context, for example, 1 million context, which can understand 1 hour long of video, we propose this streaming LLM technique. So conventionally, the memory will grow linearly as the conversation gets longer and longer. But the streaming LLM enables this very long conversation using fixed memory footprint, fixed memory budget to handle very long conversation. And that is achieved by observing this attention sink problem, where the first couple of tokens is super important. We should never evict them from the KV cache. For the rest of the tokens, we can use as attention window manner to run the attention, which is a non-traditional transformer architecture. So when conventional algorithm will run out of memory, the streaming LLM will continue streaming and working for us without leaking the memory. And it can run very long, even on the iPhone, enable this kind of very long conversation. So in summary, we've been working on model compression techniques in the context of large language model and also diffusion models for generative AI. Rather than training a model and directly deploy the model, we train the model first, then compress the model to make it smaller by using fewer number of connections with sparsity and pruning, using fewer number of bit width by using quantization techniques to reduce the computation, reduce the memory, to reject a lot of redundant work, and then we run inference on top of the compressed model, which can save a lot of cost and make generative AI available and at a much lower cost to democratize AI to everybody in the world. Thank you.